curious, slightly unsettling. Have you ever had one of those moments that felt profoundly, fundamentally off? Maybe like intense déjà vu, or a coincidence so mathematically unlikely it makes you stop in your tracks. It feels like a glitch in the system. These experiences are often dismissed as simple tricks of the light or a momentary neurological misfire. However, a group of serious physicists and philosophers are investigating them as potential systemic anomalies. They are exploring the simulation hypothesis. This is the theory that our entire reality, everything we can see and measure, is a high-fidelity computer program. In this scenario, we exist as information, and the universe serves as the hardware running the code. This image captures the Hubble Deep Field. When proponents of the simulation hypothesis look at these billions of distant galaxies, they see a precisely rendered digital structure. The evidence supporting this idea does not require new science. It comes from looking closely at the physics we already know. It requires treating the rigid, unyielding universal laws of nature as potential software architecture. To understand why this concept is a genuine physical puzzle, we have to look past the physical appearance of the universe. We need to analyze its technical specifications, breaking it down like a digital system teardown. If reality emerged through random chance, we should expect some variation in its basic rules. Over vast cosmic distances and immense timescales, the physical constants of nature would likely decay or shift. This photograph shows the M87 black hole. While a black hole represents massive visual complexity, the underlying math governing it is unyielding. This structural consistency points toward deliberate programming rather than random emergence. Take the speed of light. It is a constant, unyielding physical barrier. In computational terms, it acts as the simulation's absolute maximum processing speed limit. We also have conservation laws, which state that energy and mass cannot be created or destroyed, only changed from one form to another. These behave like strict computational budget constraints. This diagram illustrates what happens if a system allows new matter or energy to randomly pop into existence without accounting for it elsewhere. The hardware suffers unexpected resource drains. Eventually, the simulation becomes unstable and crashes. Energy, momentum, and electric charge remain perfectly conserved at all times. This structural balance functions as optimized source code, specifically written to keep a massive simulation running without errors. In computer graphics, if you zoom in far enough on any digital image, you eventually hit the pixel. You cannot render anything smaller than the base resolution of the display system. Physical reality has an exact parallel. At the scale of 10 to the minus 35 meters, we hit the Planck length. This is the absolute smallest scale at which space has any definable meaning. Below this boundary, our understanding of gravity and quantum physics breaks down, and space becomes a turbulent quantum foam. We lack the physics to describe what happens below that scale. A sprawling universe has no obvious physical requirement for a minuscule, hard stop that prevents anything smaller from being measured. Think of an open-world video game utilizing deferred rendering. Deferred rendering is an optimization method where the system waits to calculate detailed textures until the player is close enough to see them. By only calculating interactions down to the level required for observer reality to seem continuous, the system saves massive amounts of processing power. The breakdown of physics at the Planck scale represents the simulation's built-in minimum viable resolution, maximizing computational efficiency. The structure of physics points towards a digital framework, but probability presents an even stronger case. In 2003, philosopher Nick Bostrom outlined a logical framework known as the trilemma. The trilemma proposes three mutually exclusive scenarios regarding the future of advanced civilizations. Bostrom argues that one of three things must be true. Possibility 1. Civilizations always go extinct before they reach the technological stage to create high-fidelity ancestor simulations. Possibility 2. They reach that level but universally choose not to run them, perhaps due to ethics. Then there is possibility 3. If civilizations do not die out, and even a small fraction of them decide to run simulations, they will eventually gain the computing power to run billions of parallel universes. This creates a problem of scale. If one original reality spawns 10 billion simulated realities that feel authentic to their inhabitants, the odds that you exist in that one original reality are 1 in 10 billion. We have no evidence of a biological law that guarantees every civilization must self-destruct before reaching this maturity. Furthermore, there is no reason to assume every single advanced culture throughout cosmic history would collectively lose interest in simulation. If even 1% of them run these programs across deep time, the number of simulated minds would dwarf biological ones. Once you accept that simulations are possible, the volume of simulated data simply overwhelms the single base reality. This statistical flip makes it a mathematical certainty that our existence is code. If our universe is running on a cosmic hard drive, who or what exists outside of our physical laws, acting as the programmer? These programmers would be the gods of our physics. They might be future versions of humanity, studying their own history, hyper-advanced alien species using our universe as a research sandbox, or super-intelligent AI that outlived its creators. This creates a challenge for our understanding of consciousness. If we are simulated, we must question if genuine free will exists, or if our daily choices are merely the execution of predetermined simulation scripts. But this does not require a descent into fatalism. If our search for meaning and truth is part of our programming, then trying to understand the system's rules is our actual, intended purpose. The next time you experience an uncanny coincidence or a staggering moment of déjà vu, consider the framework you exist in. You might be witnessing a brief diagnostic check in the grandest operating system ever built.